Oh, yeah, here we go into lesson 4.4, the Fundamental Theorem of Calculus. Oh my goodness. Yo, this is the biggest theorem in all of calculus. I mean, it's so big, they call it fundamental. Let's jump into it. I love it, and it's so simple to use. So let me show you how easy this thing is to use. The fundamental question that's being asked here is, how do we evaluate definite integrals involving functions that do not bound nice geometric area? So we've been working with functions that were forming circles, rectangles, triangles. This doesn't do that. So we want to find this area from 0 to 2. That's all of this area here. I wrote area in there. That's all of that area. That's not a nice shape. So how do we find the exact area? I'm going to show you right now. Essentially, all you need to do is take the antiderivative of this. Let's start there. The antiderivative of x squared is 1/3 x cubed. Right? You add 1 to the 2, divide by that power that you get. And then I'm going to draw this little bar right here. Some people just do a straight line from 0 to 2. What that essentially means is just plug this number into your antiderivative right here. Plug that number into your result, and then subtract the result of plugging 0 in. That's it. That will give you the exact area. And when we simplify that, 2 cubed is 8 times 1/3. That's 8/3. Holy moly. So that's the fundamental theorem. I'll go over it more formally in the next little bit. And later on, I'll go over why this makes sense. But for now, this is it. To find the exact area between one value and another, you take the antiderivative of the function that is bounding that area, do a normal antiderivative, plug in the upper limit, subtract the result of plugging in the lower limit. That's it. How does this stem from areas of tiny rectangles? Well, again, what this is the height of every little rectangle. This is the width of every tiny rectangle. This means add up infinitely many of them. And it ends up resulting in this process. It's very, very cool. Again, I'll go over the concept of why it ends up resulting in the process in a different video. For now, it's just enjoying the fundamental theorem. All right, on to the next piece here. The Fundamental Theorem of Calculus, emphasis on fun. If you've got the integral from a to b of some function f prime of x, the derivative of some function with respect to x, then that's going to be equal to f of b minus f of a. That's it. And I wrote it down in quotes here. The area bound by the curve, or bounded by the curve, f prime of x, f of x, whatever you want to call it, the x-axis, x equals a and x equals b, is the change in the antiderivative's values from a to b. That would be f of b minus f of a. Very simple. And this finds, again, the net signed area, all of this. Now, to be very clear, what does the process find graphically? The net signed area, right? So what that means is all of this plus all of that, and that would be negative right there. And the question is often asked, why is there no constant of integration, no plus c? Here's why. If you were to integrate each of these, right, and you got something with f of x plus c minus, and then you did f of x plus c. So you find the antiderivatives and you subtract them. What happens to the c values? They completely cancel out, and then we're just plugging in b and a into f of x, giving you f of b minus f of a. That's where c goes. It's very important to note that this value here does not represent the true value of the function, right, at that x value. So what does that mean? Well, without that c value, we don't know where that function has rose or fallen to. And if you're listening to me being like, dude, Groden, what are you talking about? Then forget it. All right, I'll go over that down the road. For right now, just know that the integral of any function is equal, from a to b, is equal to the antiderivative of that function. You just plug in the upper bound and subtract out plugging in the lower bound. It's simple. Oh, it's so simple. We're going to now hit that up with 3 consecutive problems just to show how easy it is. So this right here is equal to the integral from 2 to 5 of x to the negative 2 dx. All right, the antiderivative of this is x to the negative 1 all over negative 1. And that's evaluated, some people do a straight line, some people do brackets, from 2 to 5. I'll mix it up. So you plug that in. Now I'm going to get rid of that negative exponent. So it's going to be negative 1 all over x evaluated from 2 to 5. That's equal to negative 1/5 minus, that minus is part of the fundamental theorem, a minus 1 over 2. So that minus again is part of f of b minus f of a. Just plug them in. This simplifies to negative 1/5 plus 1/2. Well, okay, so what's negative 1/5 plus 1/2? That's equal to negative 2/10 plus 5/10, or 3/10. And that represents the area from 2. Yeah, can we fit that in there? To 5, all of that. That's the exact area. Oh, it's beautiful. All right, let's do another one. So the integral from 0 to 4, the definite integral of 1/2 x plus root x. Okay, so let's integrate this. That would be x squared over 2 times 1/2, or 1/4 x squared. If you need help going over how to integrate, anti-differentiate, go back to lesson 4.1. All right, that'll really go over it. For right now, we're just doing the fundamental theorem of calculus. X to the 1/2 is what that is. I add 1 to that. That's x to the 3/2. Divided by 3/2 is the same as multiplying by 2/3. And that is evaluated from 0 to 4. All we got to do is plug in 4. So that's 1/4. I'll put a parenthesis here to group things down. 1/4 times 4 squared is 16. Plus, plug 4 into here. The square root of 4 is 2. Cubed is 8. Times 2 is 16. And then we got thirds. That's f of b minus f of a. Well, if I plug 0 and actively plug it into there, just in case it doesn't equal 0, but 0 squared is 0, 0 to 3/2 is 0, all of that is 0. So that'll be our answer. We'll simplify it down. That's 4 plus 16/3. That simplifies down to 28 over 3, right? 4 is 12/3 plus 16/3. That's the area from 0 to 4, the exact area. Oh my goodness, it's so simple. And what you're doing here is you're adding up infinitely many tiny rectangles. That's quite a lot of work with not a lot of work to do. Pretty cool. Love it when that happens. All right, does it work with trig? Yeah, it's a continuous function. So it works with trig. We're finding the area from pi to 3 pi over 2, this. So we're going to expect our answer to be negative. Everything's below the x-axis there. Between that curve and the x-axis. Well, we can factor out that 6 if you want. I'm just going to kind of hold it there. And I'm going to anti-differentiate. So that's going to be 6 times a minus cosine x. Because the derivative of cosine is negative sign. We need that negative to make it positive sign. And that's going to be evaluated from pi to 3 pi over 2. Okay, let's rock and roll. So we'll plug in 3 pi over 2. 6 times negative cosine times 3 pi over 2. That's the first value that we're doing. That's f of b. Minus, we're going to plug this in now and evaluate it. 6 times negative cosine times pi. Well, negative cosine of 3 pi over 2, cosine of 3 pi over 2 is 0, so the whole thing goes to 0. This is going to be a minus, a lot of negatives here, minus cosine of pi is negative 1, times a negative 1 is positive 1, times 6 is 6. But we still have the negative there from f of b minus f of a, the first fundamental theorem, so that's equal to negative 6, which is the actual area from here to here. Get out of here. That is just so cool. We just added up infinitely many tiny rectangles. Oh, in a much later video in this lesson, we'll go over why this process makes sense. Why does the antiderivative with those upper and lower values plugged in give us the exact area? We'll see that. For now, though, all you really need to know is the process. In most classes, you don't need to know the why. But I'm determined to show it to you. All right, that was fun. Peace. If you hung around a little bit longer, I got a little bit of a secret track at the end of this video. It's a little poem I like to call Goodbye R-Sum. I always read it after we're done with the fundamental theorem. Goodbye R-Sum, it was nice to have known you. We've used your concepts and will never outgrow you. Please forgive us as we move on to the new, better, more efficient analysis. Turn our world a brighter hue. Do not worry nor turn a sad shade of blue. We will use your midpoint approximation in May, as you know we always do. So good for the data, with no function we still have a clue. Goodbye R-Sum, and no offense, we will not miss you. I hope that was fun. Little poem I concocted for my classes and for you.